Thank you, everybody, for coming. It's always nice to see interest and people interested in hearing a little bit more about the research we do here. My name is Sam Silverstein. I have been working for many years here at Stockholm University on the ATLAS experiment, one of the Large Particle Collider experiments at Cern. We have a pretty large group here working on particle physics and on the ATLAS experiment. I'm guessing that a number of you may have come to some other lectures in the series. One of my colleagues, Sarah Strandberg, has given a talk a couple of times about the physics and the science that we study and we learn about at ATLAS and particle experiments. And so I'm going to not go into too much introduction about particle physics itself, because I want to talk about a part of these experiments which you don't usually see in a general lecture like this. So many of you may be familiar with some of the physics and the discoveries that have come out of the ATLAS experiment and the LHC at Cern, for instance, especially the discovery of the Higgs boson in 2012, which gave Nobel Prize to Higgs and Engler, and where both experiments, general purpose experiments, ATLAS and CMS, had both seen this little bump in the data, which turned out to be a particle that had been predicted and searched for since the 1960s. And Sarah and others have probably have already presented some of the physics, some of the the basic ideas behind the particles that we're looking at and the physics we're looking at. But along the way, you've also probably, many of you, seen pictures like this, the Large Hadron Collider. This is the particle accelerator where we discovered the Higgs boson, a huge circular ring as much as 100 meters underground, 27 kilometers in circumference, huge machine, accelerating particles, protons, and heavier nuclei at the highest possible energies that we've been able to manage so far. And you may have also seen some of pictures of these really massive experiments underground where we studied the collisions between particles created by the Large Hadron Collider. And a lot of my work, a lot of the focus of my work has actually been on the experiment itself. And what I wanted to talk to you tonight is not so much the physics, but I want to talk a bit about these particle detectors, these large detectors that you see pictures of that are producing these new physics discoveries, and try to explain to you a little bit about how they work and what they do. So here are the frequently asked questions when I talk to people about the work we do at Cern, and I show you these pictures of the LHC and these experiments. First of all, with the LHC, you see a big ring, and the question is, how do they work? How do you make a big machine which accelerates particles to such high energies? And when I show you pictures of these big experiments, your questions are, how are they built? How do they work? What do they do? And why do they have to be so big? Because you're looking at some of the tiniest particles, the smallest physics at the smallest scales, but you're using some of the biggest experiments ever created to study them. So why do you need to make them so big? And what's the connection between how these detectors, that are seeing these particles, colliding and measuring the particles that come out of these collisions, and how do you use that data to discover new particles, to understand the data and make discoveries like the Higgs boson? So these are the questions I'm going to try to address a little bit and explain, and I'll do my best, but if you have any questions or anything doesn't make sense, feel free to ask as many questions as you like. So let's start with the LHC, Large Hadron Collider. What is a particle accelerator? Now, I've been doing this for a long time, so when I was a lot younger, I could tell somebody that you had a particle accelerator in your house. Your television set was a particle accelerator. But That was last century. Everybody's got flat screens now. But the basic idea is that behind the old cathode ray tubes is that you had a source of charged particles, electrons in the old television sets, and you had an electric field which would fire the particles and accelerate them, make them go faster in the direction you wanted to. And then you could bend them, you could change their directions using electromagnetic fields. I don't have a old-fashioned television set to show you today, but I thought that I would do the next best thing and show you a short a video I made of a classic experiment you can do in college, which for measuring the mass of the electron. And basically, it is a glass sphere with a very thin gas inside, and you have an electron gun, something which fires the electrons with an electric field, and then you have these magnetic coils which bend the path of the electrons. So, let's see. Here is one of the setups that here we go. I'll go and skip forward a little bit. So, turning down the lights. 20, okay. So right now I'm about to turn on the electron beam. So I basically I've got this glowing cathode down here which creates a bunch of electrons, and then you create an electric field which accelerates these electrons upward. And if there's no magnetic field, of course, they just want to go straight. But of course, we want to actually change their path. We want to bend the field. So what I do is I turn on the magnets, and as I increase the magnetic field strength, the circle gets smaller and smaller because you're bending them more and more. Now, if I turn up the energy of the electron beam, so higher voltage, make them go faster, it's a little bit harder for them to bend. So you see, you have to increase the magnetic field a little bit more to get them down to the right, to the radius you want. So here I've shown you a demonstration of a system where I'm accelerating electrons and I'm moving them around in a circular direction using a magnetic field. And there's my particle accelerator. Easy, right? But it's not so fast, because if you look at this setup here, the electron beam I just showed you, I was accelerating it with a couple of 100 volts. And so the energy of these electrons is what we would call a couple hundred electron volts. Now, the energies that we're talking about at the Large Hadron Collider is beams with 7 trillion electron volts. So to make something like this work, at LHC energies, you'd have to have 7 trillion volts across this gun, and this is, for many reasons, just not possible. Okay, so you have to be a little bit smarter to get higher energies. And there are different approaches to it. One is called the linear accelerator. And here, you start with your source of charged particles, electrons or protons, and you accelerate them and get them going faster. And then you get another accelerator after that, so another electric field, which makes them go faster and faster. So as they go through each stage, they get more and more energy. Now, there's a little bit of a twist in here, that you have to turn it on when the electrons are in between the plates and off between them. So you turn it on and off and on and off and on and off, and you can, if you get enough stages and a high enough voltage, you can get a reasonably high energy to an electron beam. But it only goes through once. So linear accelerators are very useful, but it does mean that you can really only use them once. You fire them and then you can't really use them again. And also you have to get a really, really long accelerator to get to high energies like trillion electron volts. So another way of doing it is have your single kicker here, or just a few of these places where you're accelerating the electron and magnetic field, but then you use magnets to curve the path, so make it go in a circle. So it goes through and circulates again and again and again, and each time it goes through, it gets a kick and goes faster and faster. Now, if you look at, this is a little bit dated diagram of the accelerator complex at Cern. Cern is not just the LHC, it's got a lot of different accelerators and experiments, and it's also been built up over time. So a long time ago, this PS, proton synchrotron, was the big accelerator, and then we built a bigger one called SPS, and then LEP and LHC. And we use so we do things sort of in stages, where you use each stage to increase the energy more and more and then send it on to the next beam. But the protons start in a linear accelerator, gets boosted in this one, gets boosted in this one, and so on. But we use different stages of both linear and circular accelerators to get the protons to the high enough energies. Now, when I said you had to turn these accelerating parts, the accelerating cavities on and off, it's not quite like turning on a switch. What we use is microwaves, because microwaves get bigger and smaller, go up and down, just like regular waves. And you could even think about these working like almost like waves for a surfer. So in each of these cavities, you see a wave which gets bigger and smaller at a certain speed. And as the proton goes through each of these cavities, the wave sort of rises behind them, and they surf. They get a push off the front of the wave and get accelerated forward. So these cavities are one of the cavities that goes into the LHC. It's superconducting, because there's a lot of energy that goes into them, and we have long strings of these at various places around the LHC ring. So as the protons circle around and around, they go through these and they get more and more energy. And this is the way we accelerate them and keep them at the at the 7 TeV energies. So these are the accelerators, how you get them going fast. You also have to keep them going in a circular path, not a straight path. This is I apologize for the low res quality of this picture, but here is a sort of slice of one of the magnets which bends the path of the electrons in the accelerator. And so we have two beams of protons. We have, because we're colliding them together, so we have to have one proton beam circulating one way, one proton beam circulating the other way, and then you bring them together so they hit each other head on. And one of the very genius things I would say about the LHC design is that unlike previous accelerators, we had two separate sets of beams and two separate sets of magnets for the protons going in different directions. This has got one set of magnets with two beam pipes, and one beam has protons coming like out this way, one going the opposite direction. And you have to have opposite direction magnetic fields. So like, for instance, you would have the field going up on this side and down on this side. And it's a very ingenious solution where you have a circular magnetic field in this direction. So it's going up to bend the protons coming out of the board and down going, it keeps both same charge beams going around the same 27-kilometer around ring. And this would be like I said, a bad cartoon of the LHC tunnel, showing about the size of the magnets comparison to the tunnel it's in. Here's a picture I took at Cern a long time ago, showing a little slice of one of the sort of insides of one of these magnets, where you can see these golden parts are the superconducting magnets, the electromagnets, which produce the magnetic field. You have some iron around it to shape the magnetic field, so it goes around in this circle. And then you have this really, really massive steel cladding outside just to hold the whole thing together because of all the tremendous forces. Here's part of the magnet assembly and testing facilities. There were about 1,600 magnets total, or are about 1,600 magnets total in the accelerator, and they all had to be individually built and tested, and then brought down into the tunnel and assembled in place. And here's one of my favorite pictures. Something many people don't necessarily know about or appreciate. This is part of the tunnel which goes around 27 kilometers in a circle. And it's not just a matter of taking the magnets, setting them up there, bolting them together and running it. This is a precision instrument that even has to be adjusted continuously for the tidal pull of the moon on the accelerator. And if anybody of you is familiar with surveying, generally you have to measure the distance between points. You have to have line of sight. You can't do that in a circular tunnel. And yet, the engineers and the personnel at Cern have managed to survey this entire accelerator in this tunnel to better than millimeter precision. You come up with these things, they're just amazing. Here are some other numbers. Like I said, the circumference is about 27 kilometers around. 1,600 superconducting magnets, very strong ones, about as strong as we can make with this kind of superconductor. Typical magnet camera and MRI camera is maybe 1 or 2 Teslas. This is a field strength of more than 8 Teslas at full energy. And you have to cool this whole thing down to 1.9 degrees above absolute zero with about 100 tons of liquid helium. We're one of the biggest users of liquid helium in the world. The total beam energy, 362 megajoules. It's enough to melt a ton of copper. You don't want to put your hand in there. Not that you could, but. And the beam pipes, because we're circulating these protons around at such high energies, we don't want anything in the way. So we have to have a really high vacuum. And as a matter of fact, this is probably the highest vacuum in the solar system. The pressure inside these is 10 to the minus 10 atmospheres, which, to illustrate, would be about 1% of atmospheric pressure if you were standing on the moon. And we also have not just one proton going around. We have to have huge numbers of collisions to get the high statistics data we need to get the physics out of this machine. So we have proton bunches passing through each other at 40 million times every second. And each time proton bunches pass, there are multiple collisions. We have maybe, it was designed for about 25, and we're probably going to, by the time we're done with upgrades, have between 1 and 200 collisions per bunch crossing, just so that we can get all of the proton collisions we like. So the numbers are absolutely massive, and it's one of the really cool things about working on an experiment like this. So that's the accelerator. And as I've said before, it's about up to 100 meters underground, and it's designed to produce collisions. So, and you want to get something out of those collisions. So around the beam, there are different underground caverns or halls where we have these large experiments which look at the collisions and try to get the physics out of it. So I work on Atlas over here. On the other side of the ring is CMS. We're 2 general purpose experiments looking for lots of different types of physics. We have ALICE here, which specializes in looking at heavy heavy nuclei collisions for nuclear physics. And we have LHCb, which does some very precision tests of some conservation laws, trying to understand, for instance, why there's no antimatter not very much antimatter in the universe. So in these halls, we have beams which come in both directions, and they produce collisions in the center of the detector. And when they hit, they send sprays of particles coming out. And we want to try to measure all of these particles coming out so that we can try to reconstruct what happened in the middle. And so what I want to talk to in the next section of the talk is what these are made of, what these different measurements are being made as the particles leave. And I'm going to use Atlas, my own experiment, as an example, but what I want you to understand is that every one of these particle experiments, it's a custom machine, it's a custom design, and different groups of people come in with different ideas. They build it in a certain way to try to get their best idea of how to get the physics that they're looking for. But in general, if you go to any particle collider experiment, be it at LHC, being at other colliders in the world, nuclear physics experiments as well, they have basically the same things. So I'm going to talk about Atlas, show you Atlas in specific, but I'm also going to try to tell you about how, in general, things are done. So if you can come away from this not just understanding my experiment, but pretty much any particle or nuclear collider experiment, because all the pieces are pretty much there. So, like I said, here's Atlas, my experiment. It's about 25 meters diameter cylinder, about 40 some meters long. You can see some people here for general scale. And in the middle, okay, here you've got where the beam pipe is, right down the center. In the middle of this experiment is where the particle collisions happen. And as they leave, they go through different layers of detectors, and each detector layer tells you some more, it gives you some more information about the particles and what's happening. So the very inner layer, right outside of the collision point, is what we call the tracking detector. We look at particle tracks with it. After the tracking detectors, we have these detectors here, which are called calorimeters. Calorimeters, which they're detectors which measure energy, particle energies. And there's another set of detectors around the calorimeters. They're called Muon detectors, and this is because most particles can be stopped and measured at the calorimeters, but there's a certain type of particle called the muon. It's like an electron, but a lot heavier, and it's the same. It's one of the main kind of cosmic rays that come out. They can just plow through huge amounts of material without stopping. So we have special detectors to also measure them. So what I'm going to do in the next part is go through these different layers and explain the principles behind them and give you some pictures of what we're doing with them. So, like I said, the inner detector, or the tracking detector, this detects and reconstructs tracks from charged particles that are leaving the collision point. And we use this to find out what direction the particles are going, what their momentum is, what their electric charge is. And part of the way we do this is by having these tracking detectors in a strong magnetic field, which bends the particle tracks. Just like I told you for the when I was talking about the accelerator, if you have a higher energy particle, you need a stronger magnetic field to bend it, or if it's the same magnetic field, a faster particle will go straighter. So the inner detector has these tracking sensors and also a strong magnetic field, usually. Outside those are calorimeters. These absorb the particles, and it measures how much energy they had. And something else that we do is we also can find missing or unseen energy. Some of you may have seen, have heard about neutrinos, for instance, which are particles like we measure at AMAND at the South Pole, which are so difficult to detect. They can go through a whole planet without actually touching anything. So generally, you're not going to see them in this kind of experiment. But if you see an imbalance, if you see a lot of momentum going one way and nothing going the other way, then, action and reaction, you can assume that there was something that went this way that you didn't see. So calorimeters will also tell you a little bit about these invisible particles, the ones you couldn't see. And finally, the muon detectors. Like I say, they measure the muons, which we can't measure any other way. So far, so good? Good. So let's start with the inner layer, the tracking detectors. This is one of my favorite pictures for explaining this. You look up in the sky and maybe there's a plane that's really distant and small, far away that it's hard to see. But as it goes through the air, it can disturb the air, disturb the moisture in the air, and leave behind a visible track, which gives you an idea of what direction and speed it was going. So tracking detectors, you don't want to stop or slow down the particles or mess with them, but you want to set up a detector where they go through, and as they disturb something, they leave behind a signature that you can see. Now, there are two basic types of tracking detectors. There are variants on this, but I guess the original types, and still used in many places, are gas detectors, where you have a chamber or a tube in this case, which is filled with some kind of gas, like argon, for instance, that as a charged particle goes through it, ionizes the gas around it, creates charges, which then can be attracted to like wires which are held at a high voltage. And so as the particle goes through here, it leaves behind a trail of ions. The ions get pulled towards a high voltage wire and hit it, and then a small amount of charge hits it, so it produces a little voltage, a little electric signal that you can use to say, okay, we found something, we saw something hit at this place in the detector. A more modern detector element or type of tracking detector is semiconductor trackers, where you can take a wafer of a semiconductor like silicon or maybe gallium arsenide or carbon. There are different ones, but silicon is very common because it's cheap and easy to work with. And so what you do again is you you take a wafer of silicon or some semiconductor, you put some sensors or electrodes on the sides of it, and as a charged particle goes through, it ionizes the atoms in the silicon wafer, and those charges then get brought to the sensors. You get a little electrical pulse, and you can see that there was a particle hit there. So Atlas is the current. We're going to switch out the tracking detector in a few years, but the original one, the one that's still there, has both gas and semiconductor detectors. So the very center has got something called the silicon pixel detector. These are small pixels like you can think of like in a digital camera. And outside is another set of silicon trackers, but instead of having pixels, square pixels, we have strips of sensors going in different directions. So if one goes through a strip going this way and this way, where they cross is telling you where the hit was. And then we also have at the very outside, it's these gas-filled straw tubes. They're tiny thin tubes with wires in them and gas in them, and they are used to measure the tracks. And also they're designed to help you do some better identification of what kind of particle it was. Different experiments use different versions of these and in different configurations, but they use something like this, made of gas and or semiconductors. So here's some pictures of the ones at Atlas. Here's the inner pixel detector, which is quite small because it's right around the beam pipe. The supporting structure is made of carbon fiber, very lightweight, strong material, because you don't want to have anything which is too massive, gets in the way of the particles and disturbs them in their path. You want to have something very lightweight that can measure their tracks. And around the pixel detector, here's the silicon strip detector. You can see these over here, maybe is the best way, these wafers, these rectangular wafers of silicon, which are like scales, so they're overlapping so that there aren't any cracks in between them. Out here, are all the different cables which bring out the signals to read off the detector. And out here is part of the straw tube, or the gas detectors on the outside. You can see here that this is sort of a barrel-shaped piece with these little straw tubes, like I was saying. And surrounding that is this big superconducting coil magnet, which the whole tracking inner detector fits inside of, and creates a strong magnetic field to curve the paths of the charged particles. So here's a simulated tracker event. Again, I apologize for the low resolution of this, but this is a simulated Higgs boson event where you can see the different layers. So right in the middle is the beam pipe. Around it, where the tracks are the most dense, is where you have the pixel detectors, and then you have different layers of these strip detectors, also semiconductor, and the straw tubes on the outside. And the computer processors take the different hits and they reconstruct the tracks. Now, I'm going to come back to one of the first questions that I gave you. Why do these things have to be so big? I mean, you saw the size of this tracking detector, which is just the smallest inside piece of the detector. Well, as you get to higher energies, you get a lot of more particles coming out of a collision. And especially, like I told you, you're producing multiple collisions per second, or per crossing. So there's going to be a lot of tracks going on. And if everything was all in the same place, there'd be no way you could separate out, hits with belonging to one track or the other. So we have to build these things so big and with such high resolution so that we can actually distinguish different tracks. Here is a picture of of a Higgs event. Which is, what was the year in this? This is 2016, so not so old. Which had a Higgs boson along with 25 other proton collisions that happened at the same time. Now the other ones are uninteresting. They're low energy, but still they produce tracks that you have to and hits in the detector that you have to separate. And so you can see here. These are the reconstructed vertices, the collision points of all these different collisions. And this one here with the yellow lines coming from it, that's the one that we're interested in. So this is why we have to build, one of the reasons why we have to build such a big detector, because we have so many particles coming out that we have to be able to tell them apart and have them all hitting in the same place. So that was tracking detectors. Let's go on to calorimeters. Okay, so now they've left the tracking detector. This is another picture I kind of like when I'm describing calorimeters. Well, I don't know. Maybe some of you in school also did a calorimeter experiment like this, like when I was growing up in grade school, where we basically had an insulating cup filled with water, and we had a thermometer, and you would put something, for instance, something warm inside it, or if you want to be more if you wanted, for instance, do a chemical reaction and which gives off heat, you can have that inside this styrofoam cup filled with water, and the water absorbs heat from whatever you have inside that cup along with the water. So one of the things the calorimeter does is it takes and absorbs energy. The second thing you need to do is once the energy is absorbed, you have to know how much energy was absorbed in that experiment. That's why you have a thermometer, which you stick into the water as well. So in the case of this grade school calorimeter, the water absorbs energy, and the thermometer then rises, and it tells you how much energy was absorbed. Okay, so stick with me here. Okay. Now, we don't use styrofoam cups and water, but you can think about the same concepts being important in a calorimeter at a particle physics experiment. In the case of high-energy particles coming, you have to absorb them, you have to stop them, which means you have to have something really dense in order to slow down and stop a high-energy proton or electron, or going at billions or trillions of electron volts. So I've got these gray lines of absorber material, like I said, a very dense material. And what happens is if a particle hits this dense material, it'll I'll use a non-scientific term, splatter. It'll hit some of the atoms in the material. It'll produce another spray of particles as it slows down. These particles then keep going deeper, and they turn into other particles, and you get what we call a big particle shower. And eventually, all of the energy has been absorbed and turned into showers of secondary particles, and the calorimeter has absorbed the energy of this initial particle. But then we have to figure out how much energy was deposited. So in addition to having absorber material, we have something called an active material, and I have these sort of ugly yellowish color squares, which along the way, they sample the energy being left behind by these showering particles. and produce a signal which tells you how much energy there was. So you got the absorbed material and collector material. So the absorber material has to be really dense. So calorimeters are typically made with things like iron, lead, copper, tungsten. The experiment that I worked on when I was a graduate student was made out of depleted uranium to absorb the high energy particles coming in. And then the collector, the thing that measures the energy. There are two different main ways of doing it. One is called scintillator detectors. Scintillators are liquids or plastics or crystals which give off light when energetic particles go through them. And the more energy goes through them, the more light they give off. And so you take the light and you bring them to photodetectors, photomultiplier tubes or photodiodes, which turns the light into an electric signal. And then the electric signal tells you how much energy there was. The other type of calorimeters are usually liquid gas, usually liquid argon. And this is, you can think about this in a similar way as the tracking detectors. The liquid argon is a little bit denser, but basically showers of charged particles go through this liquid argon gas, and they create ions. And then you have electrodes, which then collect the ions and produce an electric pulse, which again tells you how much energy there was. So ATLAS has both types of these. The inner part, the one, the first layer close to the outside of the tracker, is this liquid argon calorimeter, which has got accordion-shaped plates of lead and steel with liquid argon gas in between them. The outer calorimeter for hadrons, this is made a scintillating calorimeter. We call it the scintillating tile calorimeter. And it's made of plates of iron, steel, with sheets of scintillating plastic in between them. So a little bit closer, nicer pictures of the electromagnetic calorimeter. You can see these white lines, for instance, are the layers of lead, and in between them are spacers and places where the electrodes capture the ionizing signals. And like I said, this is, if you remember, this is the size of the superconducting magnet outside the tracker. This is the first layer outside the calorimeter layer outside the tracker. Here's the hadronic calorimeter, and here's one of these plates of special scintillating plastic, which are being put in place in between the plates of iron. And then we have long green fibers which go along the edges of the plates and transport the light away to the back of the detector, where we have photomultiplier tubes which turn the light into electric signals. So here's how we measure the energies. And here's, for scale, a wedge with a few of these wedge-shaped modules, 256 of them in the whole detector, getting ready to be brought down to the experiment hall and assembled. So that was the tracking detector and the calorimeters. Now, like I said, if you want to measure the energy of something, you need to stop it, absorb it. But we have these particles called muons, which are a bit tricky because they don't slow down very easily. Like I said, they can travel through large amounts of distance. They're charged, but they take a long time to stop. So you can't build a calorimeter which is so big that it can stop them too. By the way, maybe I should also again say, why do we have to make these detectors so big? The more energy the particles have, the more material you need to stop these things. So the bigger the detector is, the more dense material you need to slow it down. So this is why the calorimeters have to be bigger. You still can't build a calorimeter big enough to stop a muon, so we don't try. So if you look at a cross-section of the ATLAS detector, we've talked about the tracker, we've talked about the calorimeters, and then we got this big layer outside, which is the muon spectrometer, the muon calorimeter, or the muon detector, sorry. So we can't slow it down, we can't stop it, but we can bend it. We can put a big magnetic field out there, and then we can do just the same thing as we did with tracks in the inner detector. We basically take a couple of tracking detectors, which measure the tracks of muons which come in one side and out the other, and we bend them in a magnetic field. And the faster they are, the less they bend. So, for instance, here is one of the part of one of the types of muon chambers that are detector chambers which are being made. You can see they're tubes, and they're gas-filled tubes with wires in the middle, just like the straw tubes I told you before. The same principles apply. They can be a little bit bigger because we're far enough away. We don't have to, get down to really tiny resolutions, but we still do pretty good. So we have these gas-filled detectors or other types. I mean, they're different for different parts of the detector, but they basically do the same thing, measure a muon going through. And then we have magnets, and in this case this is one of these, some of the largest, superconducting coils built. One of the first ones being put into place. Many of you have probably seen this famous picture of Atlas after the barrel part of the muon magnet system had been made, where these coils create a huge, strong magnetic field circulating around through the muon detector. And then we have these tracking chambers that I showed you that are being inserted in the inside and the outside to measure things, and some at the end. I'm going a little bit over time, but I hope that's okay. Now I've showed you the different detectors and tried to explain to you how we can detect and measure different types of particles in these different layers. Now, what I said I would do next is to try to give you some feel for how to understand how does this connect with the bump we saw at the beginning of this talk, the discovery of the Higgs boson and the measurement of different types of particles at LHC. So let's talk about understanding the data. You've got different types of particles coming out, going through the layers. How do we understand what's going on? So, the important thing to know is that all particle experiments basically have built with the same principle. You have your tracking detector, you have different layers of calorimeters, and you have a muon system on the outside. And you have all kinds of different particles coming out of the collision. And each type of particle is different, but each one has a distinct signature. It looks different. So electrons and photons, gamma rays, these tend to lose their energy really quick. Splatter, you could say, in the first layers of the calorimeter, an electromagnetic calorimeter. So if you see something which gives up its energy down here, it's probably an electron or a photon. And the difference between electrons and photons is electrons are charged. And charged particles you'll see in the tracking detector. Photons you won't. Things made out of quarks, like protons and neutrons, they go deeper before they lose their energy. So neutrons and protons, for instance, or pions, will go deeper into the detector and leave their energy farther away. And protons are charged, so they'll leave a track. Neutrons aren't charged, so they won't. So again, we can now tell which particles they were. And muons, they just go and go. But you can see them flying out through the muon detectors. So let's look at some real physics and try to see these different types of particles. One of the signatures we used to detect the Higgs boson, to initially discover the Higgs boson, was this decay where the Higgs boson turns into two photons, two gamma rays going in different directions. Okay, and so we looked for collisions with. Here's a particle which left its energy right at in the first layers of the calorimeter. Here's another one, and there are no tracks pointing at them. So we say these are two gamma rays. And we can tell, I'll show you a little bit later from their angle and energy, that this has the mass of a Higgs particle, Higgs boson. You can start seeing how this works. Here's another one. This is one of the golden type of Higgs events, which doesn't really show up in any other type of physics. The Higgs boson will turn into two weak Z particles, Z bosons, which in turn turn into each a pair of electrons. And so what you're looking for in this event where it is 4 electrons, each pair reconstructs so it looks like it was one of these, And so let's go and take a look at events with 4 electrons in them. And sure enough, here you've got 1, 2, 3, 4 particles which lost their energy at the electromagnetic in the front layer of the calorimeter. Didn't go so deep, and you've got this time tracks pointing at them. So we can say this is 4 electrons coming, and we can measure from their angles and energies that the mass is of a Higgs. Now that I'd like to say a few words of as well. It's not just saying, okay, well, we found an electron. It's also important that we know its direction, its momentum, and its energy. And because if you do know their energy momentum, then if you have some particles, you can easily calculate, if you assume that they came from a particle that decayed, a single particle that decayed, you can go and calculate something called the invariant mass, what the mass is of those particles. So here's an interesting plot. This was from the early days of ATLAS data taking, where they looked at pairs of muons and they made sure that the 2 muons were opposite charges. And so you say, okay, suppose you have 2 muons coming from a single a source. What would be the mass of that source? And so this was like 2010 data, so a very long time ago. But it was really interesting because a lot of these were just on lines with no real features. Maybe they were not any specific process. But you can see these bumps. So this, for instance, is a bump corresponding to a mass of the J psi particle, which was discovered in '73. And was basically clinched the whole theory of quarks being the fundamental constituents of hadrons. And here at this high level, this was because we hadn't gotten to really high energies yet. Here's the Z boson, one of the particles, neutral particles, which carry the weak nuclear force, and which I just showed you turning into 2 electrons instead of 2 muons. So by looking at bumps, we can detect the presence of particles. And so I'm going to go back to that very first slide I showed you, which had that Higgs bump. And I'm going to show you now the data taken between 2011 and 2012 of events with 2 photons coming out. And from the 2 photons, you measure what the mass would have been, or the reconstructed mass would have been. So let's see if this works. Yes, excellent. So the blue line is what you would expect if there was no Higgs boson, okay? And these dots are the actual data points. And what you can see is as you are getting to higher and higher energies, this line sort of went a little bit higher than you expected. And this is the bump at 125 or so GeV, which was part of the Higgs discovery. And it's all done by measuring the particles. They're looking at their energy, momentum, charge, what type they are, what they do in the detectors, and reconstructing things you're looking for, like Higgs. So I don't have so much more I wanted to talk about. There was one more thing. I've shown you how these detectors are built, but it doesn't necessarily address the question of how they get made. Here's a slide showing the number of the users, people working at Cern by nationality. You can see people coming from all over the globe, and I've shown you these pictures, these massive detectors, and these very, very delicate and sophisticated pieces. And it's not one place, one factory which builds these things. We have collaborators from all over the world who each did a piece and who worked on a different part of it, and who brought it all together in one place, put it together, and made it work. And I think this is a miracle. I think the miracle is that these detectors work at all. I mean, think about building something like the biggest, most sophisticated, most complex experiment in the world, made by different groups all over the world with no top-down management. And think about what would be the chances that we actually all fit together and work the way it's supposed to. You can't, except for at experiments like this. There are people who actually study us, people from business schools, sociologists to study us, try to figure out how we manage to pull off experiments, not just work, but work so magnificently. And it really comes down to the people. When you're working on one of these experiments, you have thousands of people on these experiments, and every one is absolutely committed to making it work, to get it to work, and putting in everything it takes, which is to say that you have some intelligent, cooperative, amazing people you work with, and including quite a few who I've known over many years to become friends and colleagues. And that, I think, is part of one of the other things that you don't necessarily talk about, but one of the most absolute pleasures of working on an experiment of this size. So with that, I'd like to say thank you for your attention, and I'd be glad to answer any questions.
Okay, so please wait.
What are the future plans for Cern? What experiments do you plan? What are you searching for?
That's a very good question. I mean, we discovered, of course, the Higgs boson in 2012. And in some ways, it might have been an unsatisfying discovery in that we were hoping to find something a little bit different from the standard model to give us this clue as to where to keep going. And instead, we found a Higgs boson exactly where the standard model would have put it. But the thing is that we know that already we see things that the standard model of physics doesn't explain. We know there's new physics to be understood, and there's still a lot of room to explore at the LHC energies. So we're still working on this. I'm working right now on part of the upgrade to the experiment, where the LHC is going to be have the intensity of the beam increased by a factor of between 5 and 7 times the original design value, which means we'll be producing 5 to 7 more collisions per second than we were originally supposed to, so that we can get as many proton collisions as we want and run it into the 2030s. And so I think that there's still a lot of space of space to explore, both looking for the very highest energies, getting high enough statistics at that, but also looking for things that are very rare, things that don't happen often enough that we've been able to see them yet. So there's still a very active physics program to try to get better measurements of the Higgs boson and the particles we already do know, and try to look for signatures of things which don't fit the standard model. Beyond that, there's already planning and work on future colliders. There's the International Linear Collider, which is, I hope, going to move forward soon. That will be a lower energy linear accelerator, linear collider, which will be useful for doing precision measurements of the Higgs particle, trying to measure that to much higher accuracy so that we can see if it has properties which are a little different than you'd expect. But there's also discussions on a possible future circular collider where we could go up to much higher energies, basically build a bigger ring and with higher energies so that we could increase the energy reach of particle physics experiments.
More questions?
Okay. I have heard of theories that there are other Higgs particles that would have the energy that that is 10 times the current Higgs particle. Is that anything you have heard about?
Well, I've heard of the theories.
And will you be able to search for it?
It's a good question. Directly, it might be difficult with the energies, but of course we actually can see indirect evidence of particles that are even higher energy than ones you can create directly. So the Higgs bosons you saw, the bump you saw, is what happens when you actually make it a real one in the detector, and you see it directly. But you can even get evidence for much higher energy particles from indirect evidence. So, yeah, there are multiple theories, multiple ideas of where to go. We're finally catching up a little bit to the theorists. For so long, had been working on things like supersymmetry and other theories, which absolutely beautiful theories in terms of making everything fit neatly, but which, when we turned on the LHC, didn't appear where we might have hoped. So I would say that, yeah, there are lots of people. There are 3,000 people working on Atlas, and we're all sharing the same data. And so different groups in Atlas and all the other experiments are looking at the same data set for different questions. So, new Higgs, heavier Higgs bosons, there's a group. There are people who are looking at the data and trying to see, can we find evidence for that or set limits on it? There are people looking at other questions as well. That's why we call experiments like Atlas and CMS general purpose experiments. We're designed to do really good measurements of all the particles that come out in such a way that we actually can hopefully resolve a lot of these questions. So that's certainly one of the questions that is being looked at, but not exclusively.
More questions?
Won't the particles lose energy when they go through the tracking detectors, and do you compensate for that in some way?
Also a very good question. Wow. Yeah, I mean, an ideal tracking detector would have, be massless. But in fact, you can't do that. So actually, it's one of the challenges of building a detector is you can't build a perfect one. There's always compromises. And the tracking detector is one of the big ones. You try to not disturb the particles, but of course, there's so many particles going through that something's going to hit something. So yeah, in part of your analysis, you understand that there's that the tracking detector is not ideal, and you have to study and understand the what the effects of the tracking detector are, not only on the tracks going through, but even the material behind. An example, for instance, I didn't talk about CMS, but CMS, their electromagnetic calorimeter, the first layer, these are crystals of very heavy lead tungstate crystals, clear but extremely dense crystals. And if you have nothing in front of them, they are amazingly beautiful in terms of the energy resolution you can get for measuring electrons and photons. But they have a tracking detector in front, which means that it's not quite as ideal as if you had it. So it's a great question, and all of these detectors have compromises. You have to compromise between what you'd like to do and what you can practically afford to do and what can be built with the technology you have.
Do we have more questions? If that's not the case, let's thank Sam again.
And thank you for your attention.